All right, so thank you, Giovanni, for the introduction. Hello, everyone. I'm very excited to present this project finally here, to all of you guys. And yeah, indeed, I want to talk about Heapster, a system we developed to analyze the security of dynamic allocators in monolithic firmware images. Let's start to dive in by breaking down the titles. First of all, dynamic allocator. Dynamic allocator are algorithms that are used to manage dynamic memory, in other words, like the heap memory, of any programs in general. And a robust dynamic allocator is usually crucial for the performance of any software. And it's usually composed by at least two primitives, Malloc and free. And we're going to call these two primitives, from the rest of the talk, the heap management library, the HML. Dynamic allocators are routinely abused as building blocks for complex exploitation chains, and it's not uncommon to see at point-to-one many heap-based vulnerabilities being used to put together very complex exploitation chain for different targets, like routers, like Zoom, like Google Chrome, whatever target. So these are very powerful primitives. The current research is mainly focused on allocator for classic systems, and I'm going to introduce in a bit what is a classic system, but in a few words, system like your laptop or any desktop system that we are used to. So the libc, for example, that you are using in your system. Yeah, on the other side, we have monolithic firmware, which is a firmware without an OS abstraction. So here you see a picture of a classic system in which the boundaries between all the components of a system are very well defined, and they talk to each other with some sort of APIs. When you have a monolithic firmware, and we call it with a funny name sometimes a blob, you indeed have a blob, a binary with everything inside. So operating system library, the application, and the library, supporting library, all together in a single binary. This is a monolithic firmware image. Turns out that they empower a huge amount of diverse IoT devices, and this means that the attack surface out there is indeed huge. And there is a spectrum of different threat scenarios out there, and they go from, oops, I just hacked my toaster, which, yeah, you're going to have a bad breakfast, but it's not a big deal, to, oops, I have a remote arbitrary write over your pacemaker, probably you're going to have a very bad day, so very bad scenario. This is a very hard target for static and dynamic analysis because usually you are with the binary, and you are on your own with the binary. You don't have symbols. You don't even know sometimes where the firmware is supposed to run on, so completely blind. And also, if you want to scale the analysis over hundreds of different images, there is the scalability of the rehosting technologies, which is right now still a big challenge to support all these firmware images. So pretty headache for program analysis. So what we want to do here, we want to bring together the two worlds and study what's in the middle. So the main two research questions are, first of all, we want to understand if the firmware binary is using a dynamic allocator at all, and second, if the firmware allocator is robust against known attacks. So just to define a little bit the scope of our research, we want to focus on monolithic firmware images, like I said, for Cortex-M, and specifically firmware images that are using classic allocator. And with classic, I mean they function like the Malloc you guys know. So they receive a size as a parameter, at least, to specify how much you want to allocate. They return the calculated address through a register. So in ARM will be R0. And finally, they take this opportunity to reuse the allocated chunk. So if I free a chunk, I expect at some point to see the chunk to appear again in memory, that address at least, so to maximize the performances. So we put together Heapster, which is mainly composed by these 4 steps. And our end goals are, first of all, understanding where is Malloc and free, and second, check the security of these primitives. So we start with a firmware image. We don't know anything about it, just that is for Cortex-M. And first thing first, we want to identify the basic functions, so functions that are consuming pointers or manipulating these pointers to perform some action. Then we want to find who is the source for these pointers, so the pointer sources, we call them. Third, we want to, in this subset, identify Malloc and free. And finally, check the security. We're going to dive in all the steps in the following slides. So as I said, we receive a binary blob. We don't know anything, just a bunch of 1 and 0s. The first thing we want to do is to identify the boundaries of the functions. So to do this, we use a recursive disassembly technique and just pattern matching the prologues of functions. So we go from this to this state in which some functions are defined in the blob, and we can start to make sense of what the blob is containing. Now, the problem is sometimes we have hundreds to thousands of functions, so we cannot dig into this set manually. So we need to use automatic technique to understand what's going on. The problem is, as I said, we were looking for Malloc and free, and this looks like looking for a needle in a haystack sometimes. So again, we need automatic technique to perform this task. First intuition is memory allocator generate pointers. That's their job, right? And second, pointers are eventually used to perform memory operation. We want to do something with these pointers. So the question is, who is using these pointers? And turns out this function, memcopy, memset, memcompare, and every string manipulating function are consuming the pointer. We can call them consumer. And these functions are simple to identify because they have a very basic behavior. Indeed, we call them, in our paper, basic functions. So, for example, let's say we want to identify memcopy in this jungle of function we identify in the binary. Let's say we grab a candidate, F8 in this case, on the left. Let's say we know this function takes 3 parameters. We set these 3 parameters to known input. We run the function, and we check at the end if the execution respects the behavior of a memcopy. So in other words, for example, let's say the buffer at the source is containing the buffer at the destination, and the buffer at the source is unchanged. So if this is true, we call this memcopy, and we have different models we check against all these functions. So we go from this to the state in which some basic functions functions that are manipulating memory are defined in the blob. We can also see this function as sinks, so thinking that pointers are flowing inside this function and being consumed over there. So now the question is, where are the sources? So we call the sources a pointer source because they generate this pointer and provide it to our sinks, to our basic functions. So in this example, you can see F19 returning V25 that flows inside memcopy, our sink, in other words, our basic function. To identify pointer sources, we use a static taint engine based on rich in definition, and we run this analysis in an interprocedural way to connect different points of the blob and see if there is any flow of a definition, a static definition returning from any function that defines any argument of one of the basic functions we identified at the previous step. So again, in this case, F19 is creating a static definition. Let's call it F19 return that defines the first memcopy argument. So in this case, we call F19 a pointer source. So now we have sinks and we have sources. We know that a memory allocator is a pointer source by construction, right? So the question is, sometimes I have many pointer sources, so I don't want to go through them manually again. So we want to use automatic technique to understand who is the allocator of this blob. So the first intuition, Malloc return pointers inside the heap region. And this is thankfully standardized in Cortex-M. So it falls the heap region falls between these two addresses. And second, Malloc returns different addresses to subsequent calls because we want to place different objects at different parts in memory. So that being said, we take a pointer source and we dereference it, so we get all the call site, we get the argument at the call site, and we call the pointer source a bunch of times. And then we check for every address or value that we find, that we generated, if first of all the address is inside the heap region, and second, if it's different from the previous addresses we just generated. If the answer is yes, so positive answers to both of the questions, we call this a candidate Malloc. So new state, from this state we go to having define some candidate Malloc in memory, in the blob. And now we want to find free. How to do it? So according to our research scope, Malloc and free, they work in LIFO. So they work in pair. The allocated chunk at some point is going to be reallocated according to our scope. So we use this intuition to, first of all, we select some candidates statically by using some syntactical feature of the function. And then we pair every candidate Malloc with every candidate free. Then we call the candidate Malloc X amount of times, and we generate some addresses, and we register those addresses, and finally, we feed the candidate tree over and over with all the addresses we just generated, simulating the allocation of the chunk we just generated. Finally, we call the candidate malloc again, and if the generated address is equal to one of the addresses we observed before, then we say that this is a valid pair, and we call this the heap management library of the blob. So you see, we went from this situation where nothing was known, like a jungle, basically, I like to say, to a situation in which we found like the needles in the haystack, and so we can point to malloc and free inside the binary. So we evaluated our HML identification pipeline against, first of all, a ground truth of 20 monolithic firmware images from previous work. And when everything looks good, we scale our analysis over 799 monolithic firmware images that we call the wild data set, coming from a very recent paper in the area. And specifically, I call it the wild data set because it is like extremely heterogeneous. Like there are like firmware coming from different kind of domains, so wearable, sensor, medical devices. It's very, very diverse, and we like it a lot because it's very heterogeneous, so it can give us some insight on the problem you're trying to solve. So we identified for 340 of them with Heapster. They were actually using a dynamic memory allocator. And this is a very interesting percentage because there is like a huge pushbacks from the embedded developing community to not use this technology in the firmware. So this is saying that nearly half of them are actually using one. We found like around 10 different HML families in 32 different variations. And for family, I mean, let's say, high-level implementation of the allocator, so a kind of allocator. And variations, I try to catch all the options you can use when you compile it, or customization, or any other like variation indeed of a specific implementation. When we run our HML pipeline, identification pipeline against the data set, we got something like this. So you can see that there are like some allocators like are being used a lot, the pink and the green cluster. And then there are some outliers, and we check them manually, and they are actually not similar to any allocator we observe in the others. And these are kind of the inspiration for the title of the project, which is Heapster, because these are like Heapster implementation of the heap. You got the joke? All right, so now we identified the allocator. We can call malloc and free, perform some like testing. We want to do security testing. We want to, first of all, divide between heap exploitation primitive and vulnerable state. An heap exploitation primitive is, for instance, an heap overflow. And I want to see this as like a bomb we can use to trigger explosion inside the heap library, so the state of the heap library. And a vulnerable state is a corrupted state, for example, an overlapping chunk. So chunks are like overlapping each other, so you can corrupt data structure from different objects. So the first thing we do, we generate hundreds of different POC, proof of concept, or in other words, proof of interaction of a program with the heap by creating a permutation of actions, so malloc free in a sort of like different order. And we also inject those like bombs, those exploitation primitive, heap exploitation primitive, to see if they're going to trigger any explosion later. So we create the POC, we compile it, and we use our system to load, first of all, the POC inside the system, and then we side-loaded the firmware itself, the monolithic firmware image, and we hook the calls from malloc and free to be redirected inside the firmware itself. So when we symbolically execute the POC, we are going to redirect the execution inside the firmware itself, so advancing the state of the heap. And hopefully at some point observing explosions, so some bombs are actually triggering any corrupted state in the heap itself. So we selected 32 unique HML representatives from the clusters we identified before, and we tested them, and we discovered that all the tested HML were vulnerable to at least one heap exploitation primitive. So from this graph, for example, you can see that we were able to trigger an overlapping chunk when using an heap overflow 100% of the time, so over all the HML we identified in our data set. Another interesting observation is double free was helpful only to trigger apparently an overlapping chunk for less than 75% of the blob, but was not helpful to trigger any other like corrupted state. So yeah, anyway, takeaway point, all the tested HML were vulnerable indeed to at least one exploitation primitive. So now you can tell me, all right, Fabio, but what you did, you just tested like all these HML inside an emulator. So does this translate to like the real board, so like on a real board? We actually did a further step, and we developed like an application that uses Malloc and free. This is like an STM32 board. There was a very simple application that implements some like sort of manipulation of frame coming from the network. And the embed suite, the compiler online we used to create this application included like an unknown HML that we were not in control of. And what happened is we ran Heapster over this HML, over this binary. We identified the Malloc and free, and we were able to identify possible attacks. So given some exploitation primitive, we were able to trigger some vulnerable state. So we confirmed this on the board, and by looking at the log of the board, we were able to see that chunks were allocated like out of the heap or overlapping each other. All right, let me go through some conclusions. If I want to take away some points from this talk, the three main things I want you to take home are, first of all, dynamic allocators are often using monolithic firmware images, contrary to what like the embedded developer community thinks sometimes. They are like different and unique implementation in different variants, sometimes even like very exotic implementation of the allocator. And every tested HML, like as of now, we're like vulnerable to at least one exploitation, heap exploitation technique, so we're able to trigger like a vulnerable state. All right, everything is open source. You can play like with the framework on our GitHub, and these are like some links to contact me if you have any question or like further discussion. I'm always very happy to chat about it. And yeah, that was my time. Thank you for yours. I'm happy to take questions.
So thank you, Fabio. We're a bit behind schedule, so if you have a very pressing question, please go ahead and ask, but I think we have only time for one.
Hi. A very cool talk. Just a quick question. You mentioned you had this LIFO constraint on identifying the free function. Does that bias you somehow towards particular allocators that are maybe more vulnerable? So something like an allocator that has a quarantine is not identified by your approach?
So you're asking me if the identification of free is biasing me toward identify the entire HML. So I will say no, because...
or rather that it biases you to a particular allocator.
Yeah, so I will say no, because what we observe is that this behavior, like this LIFO behavior, it's like strictly like so when you find a pair, like Malloc and free, it's always like the correct one. But now, now I re-elaborate this question, actually. Probably the answer is also yes, because because of the research scope, right? So if I'm looking for this specific allocator, so yeah, the answer is ultimately yes.
Okay, so maybe we
From
can
no
chat
to
later
yes. Yeah.
All right, thank you.
Thank you so much.